So I'm Daryl Welk. I'm CTO of Green Room Technologies. Today, I'm going to talk about generative AI, how to train your dragon. This is a hot topic. I want to thank the Austin HIMSS chapter for having us here today. How to train your dragon. So generative AI is a rising force in healthcare. We've all seen it. It's powerful and promising, but would you trust it to speak with your patients? So my experience in the AI world goes back to the early 90s at MCC Research Consortium here in Austin. I started a project called the InfoSleuth Intelligent Agent Project. We were designing and implementing distributed software agents that collaborate with people and other agents to gather and analyze information in the World Wide Web. And this meant that we had to have intelligent agents that could think like people. So we were using ontology for giving knowledge to the agents and then working in the distributed environment. My career since then has been more in the traditional database management problems world. So occasionally drawn back into the AI world. The last time this happened was a few months ago in January when ChatGPT from OpenAI went live to millions of people. To be honest with you, I was blown away by it and intrigued with how to harness its power. And I talked to Kristen Norton, our Green Room CEO, and she suggested that ChatGPT reminded her of the 2010 movie, How to Train Your Dragon. And so we have this generative AI dragon we're trying to figure out how we can harness it. So keep that analogy in mind today as we continue our discussion. The screen you're looking at now is a Venn diagram that kind of tries to cover the world of AI and how generative AI fits in. So there's numbers of subcategories of generative AI. And we're dealing with this little red box in the middle, the generative AI, or GAI. Down towards the bottom, I've got some red descriptions of machine learning, deep learning, and generative AI. Let me just cover those for a minute here, sort of set the stage. Machine learning is different from other software. So rather than programmers coding algorithms to solve a problem, machine learning automatically learns patterns and algorithms from a training data set, and then it uses that model to find patterns in future data sets to make predictions. And a good example of that in the healthcare world is creating a machine learning model that's trained on data about hospital patients, consists of patient's conditions and indication of whether that patient was readmitted to the hospital. You can then use that model when you encounter a new patient that's being discharged to predict what's the probability that new patient will be readmitted. Deep learning is similar to machine learning, but creates the model using layers of artificial neural networks to make predictions. So the artificial neural networks have been around since the 50s, but more recently, deep learning has harnessed a lot of that power in layers to do predictions. Then generative AI at the bottom then also learns patterns in a training data set, but doesn't use that to make predictions, but rather uses the model to generate new data with similar characteristics to the original data. And hence, that's the name generative AI. So in the lower right-hand corner of my slide is something called artificial general intelligence. And you'll hear this talked about occasionally, and this is kind of a hot topic and a very far future topic. And this is when people talk about the singularity, where the AI kind of takes off on its own. That's requires self-awareness, consciousness, a lot of capabilities that our AI doesn't have today. But I show it in the lower right-hand corner along with an arrow pointing to it. What's missing on my slide in the Venn diagram is something called symbolic reasoning AI. This is the other side of the world from the statistical probability AI that generative AI is. And the best example of this is a project called Psych that was started at MCC back in the early 80s by Doug Lenat. And so Psych works with symbolic reasoning. So rather than statistically trying to predict, it works with symbolic logic. And the Psych project has been building psych knowledge base for the last 4 decades. They have 2,000 person years of entering common sense and general model. So I believe it's important to take symbolic reasoning and add it to the generative AI we have. That's still not enough for this artificial general intelligence. So I sort of have an other AI. So as we move through the years, we're going to need other types of capability, whether it'll be enhancing what we already have or something new. So as I said, generative AI creates new content. The way it does that is with a kind of a process that consists of training, adaptation, and tasks. And so a large language model is what we use in generative AI. And on the left-hand side, I show estimates for what it takes to train a large language model. So a large language model can be trained on text, images, speech, structured data, 3D signals, software code. And you can look at the amount of time and effort and cost it costs, for example, to create GPT-4, which is the large language model that's used in ChatGPT. So that kind of gives you a feeling for what it takes to build one of these large language models. And I'll talk a little bit about then how do we use those models. So in the middle under training, I've got a list of some of the more popular large language models that have been developed by companies like Google and Meta. I'll talk about adaptation in a minute. So what we do, the kind of tasks we can do, can generate text, images, audio, video, software. All of these different types of new data can be generated. For example, Midjourney is a large language model that focuses on generation of images. Like the dragon image on the first slide that I have, which was generated by me just giving a description of what I wanted to see, and then it generated the image for me. Okay, so we have these large language model. It costs millions of dollars to create it. It took thousands of machines to run it. So how do we adapt it to our task in healthcare? And I like this slide. It has three ways that you can adapt a large language model. The top one is modifying a pre-trained model by fine-tuning it with smaller data sets specific to the task. So in this case, you're actually going back in and you are modifying that model itself. So this is a fairly expensive way to adapt a large language model. Typically is just done by the creators like OpenAI. In the middle is prompt engineering. And this is where a lot of the recent work by people who aren't building the large language models themselves, this is the way we can adapt that model. So a prompt engineering guides a pre-trained model by adding information to the prompt, natural language guidance for a specific task to prompt to those prompts. And I'll show you some examples of that in a little bit. And then at the bottom is modifying a pre-trained model using reinforcement learning from human feedback, or RLHF. And this is a case where, say with OpenAI, they've had a number of people who, once they have the pre-trained model, they ask it questions, it gives them answers, and they judge how well those answers are and give feedback then, human feedback to the model. So those are three different ways that you can adapt a model. And on the right-hand side of the diagram, then, what we're trying to do in that adaptation is improve the accuracy, say, for the medical domain, trying to improve how accurate it is. There's actually a trade-off between accuracy and creativity. It's part of what makes the large language models interesting is that they are creative. They're creating new information. And we don't want them, we could get perfect accuracy if all they did was just return word for word some source that they found. But it's that step of creativity where they take a source plus other information that they know about and create new information. Unfortunately, when they do that, we have to deal with hallucination. And hallucination is where the large language model actually creates new information that's not accurate, that's not true. And it looks true. It looks like it's accurate, but if you dig into it, it's not accurate. So those are kind of a three balancing act we have. Because we have APIs to these large language models, we can build systems that will access, say, ChatGPT, but not be solely dependent on ChatGPT for the knowledge, because those systems can also access my enterprise database or maybe a smaller model I've trained specifically on my enterprise data. So, and then use ChatGPT selectively to improve the interaction or to add a little bit of knowledge to it.